and you can stop at the end of the talk.
Okay. And the video after that, it's available somewhere, or?
Yeah, it will be downloaded to your laptop or desktop or whatever.
Okay. Okay, perfect.
Can you see my screen in full screen?
Yeah, it's perfect.
Okay.
Yeah. It's perfect. Okay, so there is 2 people more that are coming. Okay. Okay, I'm just waiting. I see that other people are coming. I'm just waiting 2 minutes.
Okay.
Okay, so maybe I can just introduce the webinar. So thanks everyone for joining this second webinar session. So today we are glad to have Julien Brajard from Nansen Center to give a talk about, as you can see on the screen, data-driven parameterization in numerical models using DA, data assimilation, and machine learning approaches. So I will try to record the video if everything is okay. So we will make this video available as soon as possible after the talk, probably during the week. And well, I guess that no other people are joining us for the moment. As suggested by Julien, maybe we'll make a little break in the middle of the presentation to have some questions.
Yeah.
Yeah. So, okay, it's fine for me. Julien, if you want to start, I give you.
Okay, yes, thank you, Maxime. Yeah, first, thank you, Maxime and Ronan, for the invitation to give this talk to this OceaniX project. I have seen also the other talks that are programmed on the seminar. It looks very, very interesting. And also I want to acknowledge the collaborators with whom I worked on the result I will show you today. So Alberto Carassi, Marc Bocquet, Laurent Bertino, who have worked for about the first part, the two first part of this talk. And also I will show you some an extension of those results done in the framework of PhD by Arthur Filoche with Dominique Berezia and Anastas Charantonis. So as Maxime said, I will stop at the point of the talk if you want to ask a question on the first part. But also, I guess you could ask question on the chat if there is some things quick things to say on the slide, so I can maybe comment a bit more if there are something unclear on some details on the slide.
So, yes, if you want, Julien, I will try to manage the chat, so you'll be okay with your presentation.
Yes, perfect. Okay, that's all right. Okay, thanks. Okay, so yeah, first as an introduction, I wanted to show you this curve, which is the one forecast skill with respect with the year it has been done by the European Center for Meteorological Weather Forecast. So the skill gives roughly the number of days for which the pressure is predictable in Europe. You have, of course, the same kind of curves for all the region of the world. And what you can see is since 1981, so the left part of the curve till 2019, there will be a huge increase of the forecast skill of the meteorological weather forecast from 4 days when I was born in 1981 until 7 days now in average. So the days are the day where the correlation with respect with the analysis go below 80%. And in the same, roughly the same period, not exactly since 1976 until 2015, you also have a huge increase of data that are available. And here it's an example of only satellite data that can measure the surface temperature. So you still that from 4 or 5, 6 satellites in the early 80s, we now have a dozen of satellites measuring the temperature in the late 2000 years. Okay, so I want to relate those two curves. So the point of this talk is to make the relationship between what we can do with data to improve the forecast. So this is the first question. The first big question I will try not to answer fully, of course, but try to address in this talk is, can data help producing better forecasts? So can we use data to produce better forecasts? As it has already been done, but how we can use further data to produce a better forecast. And the second question, which seems quite similar, but actually which is a bit different, is, sorry, I still have some problems to change the slide. So can data help producing better models? So it can look like a similar question, but actually there are some difference between those two questions. So better models, meaning you have a better understanding of the process, and you can better simulate the dynamics of the system you are studying. So how to improve this forecast? So it's a very rough view of that. There is several ways. You can, of course, one key thing is to estimate good initial conditions, because when you forecast, for example, the weather, you need to have first an initial condition which are the more accurate possible. You can improve your model physics, or you can have improve your models by having, for example, a higher resolution, or having good parameterization for the scales that are not still resolved in your model. So that's basically 3 ways to improve the forecast skill. And actually, data can be used to improve the forecast with these 3 manners. So the more standard one is to estimate accurate initial condition using data. And it is what is done operationally in all meteorological centers using data simulation. But you can also try to improve your forecast skill by improving the model itself. For example, improving the parameterization of the unresolved scale, or improving the model itself by emulate a part of the model using the data. So you use the data to produce a better model, or to produce an emulator of the model. So this is the part. So this second point, this is the main point forecast of a model and observation you have of the systems. So either by satellite or by in situ sensors, to improve the estimation of the state of your system. Okay. So just one quick example. I'm coming back to this difference between a better forecast or better model. And to show you that the problem is not as simple as it looks. So here it's an example of a result in a very cited paper, very nice paper actually, Patak et al. 2017 in Chaix, I think, where they have emulated a dynamical model using only using machine learning techniques, using only the output of the systems. So they don't run the true equation, they just emulate the model. So they have a reference, so they know what should be the simulation. So this is the first panel, here's the top panel. You can see my cursor, right?
Yes, yes.
Yes, okay. And this is, on the second panel here, this is what the emulator produces. And on the third panel, this is the difference between what the emulator produces and so the difference between the prediction and the two states. And what you can see is actually this emulator produce quite good forecast, because if the two systems start as the same initial conditions, so we have dropped the initial condition problems, we have the perfect initial conditions, so we only have the model error problem, and we just simulate in time both the true system and the emulated system, and you see that until four Lyapunov time, so it's quite a lot. So one Lyapunov time is a time where the one error in the initial condition is doubled. So four it's quite nice. So this system is a quite good system to forecast your state. But as you see, obviously it's not a good model, because after a while there is a blown up of the model. And actually, this kind of problem occurs a lot when you try to do some emulator using machine learning based only on data. So in this talk, I will talk about two subjects, two results we have. One is using data and machine learning to build emulators of a numerical model. And so the full model is estimated using an emulator. And on the second part, I will talk about how to using machine learning and data to improve the parameterization within a numerical model. So yeah, let's start with the first part. So what is the problem? So we just assume that we have an unknown dynamical system, which is represented by ordinary differential equation, like it is represented here. And for this ODE, ordinary differential equation, we have a resolvent, so we can, if we know the true system, we can produce the state of the system at one time step, given the state of the system xk at a previous time. So what is the objective? We don't know M, which is here our model, and we try to emulate this model M using a data-driven model, GW, which is represented by a neural network. And how it can be done? Okay, I'm sorry, I have a background noise in my house. I will try to give me just 1 minute, because it will be very annoying otherwise. I'm very, very sorry.
Yes, it's okay, Julien, no problem.
Yes, sorry for that. Can you still hear me?
Yes, it's fine.
Yes.
Perfect.
Okay, so sorry for that. Yes. So the objective of this work is to produce this, to emulate this model M by a data-driven model, GW. So typically it can be represented by a neural network. And so what we want to minimize is the difference between what is actually observed, so the X, the state of the system, with what our emulator is simulated. So we want our emulator JW to simulate the best possible system. Yeah, on all the time, all the available samples we have of this system. And actually, this is what has been done in the Patak paper. So afterwards, they have tried. Of course, they have succeeded to stabilize their model. So this is the final result they have. So they have both a good forecast and a good model at the end of the paper. And you see that if you observe the true state, so you observe xk, you are able to make some very good prediction. So here again, on the left part here, you have the initial state of x, and you will simulate both by the true model, because in this case you assume you know the true model. It's what is called the twin experiment. So you know the true model, and then you forget it to train your neural net, but you know it, so it can allows you to assess the result of your prediction. You have your prediction, and you see that it's pretty good. You have a good forecast, and at the end, even if you look at the field by the true field and the predicted field, it's quite you cannot tell the difference. And actually, it's true that you have produced a good model, because you can tell by looking at, for example, Lyapunov exponents, or by looking at spectral density function, that you have states that are very, very similar. Oh yes, the system here is a Kolmogorov Smirnov. I'm not sure. I'm not so sure, but it's a small dimensional chaotic system. Okay, but now this is the result you have with perfect X. So you know exactly the state of the system you want to emulate. But now let us consider the case where you don't know perfectly the state of the system, but you know some observations on this state. And when you observe a state, you don't observe everywhere, and you don't observe with perfect accuracy. So what you observe is only for example, a subsampling of the X. So there is a mapping between the state of the system and the observation. So this mapping is done with an operator which is generally called the observation operator in data assimilation. And you have an additive noise here. So we assume that we have an additive noise, Gaussian noise. So now we have two difficulties, because we don't know the dynamics, we don't know our model, but we don't know either the state of the system X. So we have two unknown to be determined. So the idea to overcome this difficulty is to combine data assimilation. So when I say DA, from now on it means data assimilation, and ML, which means machine learning. So combining those two tools to develop accurate emulator for imperfect data, so noisy and sparse data. So why would we do that? So the idea is data assimilation is quite good as estimating the state of the system in an objective way. I have mentioned it already in the introductions. When you want to estimate good initial condition, you can use data assimilation. And data assimilation is also quite good at estimating the uncertainty of that state. But data assimilation needs a numerical model to combine the output of this numerical model, the forecast of the numerical model, and the observations. On the other hand, we have machine learning, which we know that are very good to retrieve some hidden relationship in a data set. But machine learning needs, as the name stated, a learning data set. You have to learn you have something to learn from. So actually those two tools are quite complementary, because data assimilation is good to produce a learning data set, and machine learning is good to produce a model. And actually this idea is not new, and it has been applied in a series of papers. So it's not a comprehensive list. I have mentioned the paper where I'm involved in. Also this Abarbanel paper, which makes the equivalence between data assimilation and machine learning. And there is also a paper recently by Nguyen, I think is here actually, he attended the seminar, which also made this point and use this idea. So you have more detail about that in the paper of Brajard et al. 2020. And so I will just go a bit more into detail. So how we do that. So I remind you that the objective is to emulate the resultant of a model, so M, by approximate it with a neural network GW. So G is a name, if you want, of the neural network, and W are the parameters, or sometimes called the weights of the neural network, with an uncertainty epsilon M. And so we propose a cycled algorithm. So we will alternate between a data assimilation step that aim at estimating the state of the system, and a machine learning step which aim at estimating the model, or more precisely, the parameter of the model. So we initialize those parameters randomly, and then we have a first data assimilation step using this very bad model, because with random weights you don't have a good model, but still with a bad model you can use this bad model to estimate a first guess of the state of your system. From the first state of the system you can estimate a new version of the weights, and then you cycle on that. And so you hope that you will improve both the estimation of the state of the system and the model. And when you have converged, you stop. So if you want to see more in detail how it works, so the data assimilation estimates the state field here, which is called analysis in the data assimilation field, and also the error of this estimation, P, but it's based on model parameters W, and of course on the observations. And then in the machine learning step, you use this estimation of the field X, and you also use the estimation of the uncertainty P to estimate the weight. So I won't go too much into detail, but something to remember, the neural network has a special structure here. So we don't really estimate the full resultant of the model, but we only estimate the increment. So we estimate what has to be added to X to produce the next step. And we use this loss function to minimize or to train our neural net. So we minimize over several forecast steps. And also note here that we use the covariance matrix determined by data assimilation to give a weight to the target. So the targets that are more certain will have a stronger weight, and the targets which are more uncertain will have a weaker weight in the evaluation. So the neural net will give more importance to the target is more certain of. Yeah. So this is the algorithm. And so I will show you just the one result using low dimensional chaotic model, the very broadly used Lorentz 96 model. So just quickly the setup of the experiment. So we know the true model, but we only observe from one long simulation. We only observe 50% of the space. So at each time step, each observational time step, we observe 50% of the states, and with an additive error. So you see here that the error is actually quite not neglectable, because you have values of the state that goes approximately between -10 and 10, and you have errors that goes between -5 and 5. And on top of that, you don't observe all the state. So it's truly a noisy and sparse observation. So this is the neural net we have used. So there is a relatively low number of weights to estimate for modern machine learning problems. We have 3 layers neural net with 1 layer which is bilinear, so that impose a multiplication to be done. And so this is how the algorithm converges. So I remind you that the algorithm works onto several cycles. each cycles include one data assimilation step to estimate the state of the system and one machine learning step to estimate the weights of the parameter on the model. So here is the result after one cycle. So after one cycle, you see what is your true simulation, what is the simulation starting at the same initial state for the surrogate model or the emulator. And this is the difference between the two. And here on the left part, we represent in blue the root mean square error of the forecast after one time step, and in orange, the first Lyapunov exponent of the surrogate model. Given that the first Lyapunov exponent of the real model, the actual model of the truth, is 1.67. So you see that after one cycle, it's not that good. Actually, the surrogate model gives you something which looks very periodic waves. It looks like periodic waves. The RMSE, so we cannot tell if it's good or bad, but it's not so good. And the Lyapunov exponent is quite far from the true value for the Lyapunov exponent. But then you cycle over several. You alternate several times DA, machine learning, DA, machine learning, DA, machine learning. And this is what you obtain after 50 cycles. But actually it converged after around 35 cycles. And you see that when you cycle a lot of time, you converge toward the lower root mean square error for the forecast. And you see that you have forecast scale until 2 Lyapunov times, so it's not that bad. And you see that your Lyapunov exponent is converging to with some bit noise, but to the true values. And you see that the simulation of your surrogate model is very similar to the simulation of the true model. So now, if we want to come back to the two questions, do we achieve good forecast? Do we have a good model? So here I will try to see if the model is similar to the true underlying dynamics. In that case, here in the case of a twin experiment, so we know what we should have as a true underlying dynamics. And the first indicator to show that is the power density spectrum. So it gives you for each time frequency how much energy there is. So you see here in blue the true model power spectrum, and in the gray here the surrogate model power density spectrum density after one cycle. So you see that there are some peaks to some frequencies. Some frequencies are favored. And so this is quite consistent with this wave propagation we have seen on the previous slide. But then in orange you have the power spectrum of the surrogate model after convergence, after the 50 cycles, and you see that up to 5 hertz you reproduce the surrogate model is reproduce very well the true power spectrum density, and it's not you add some high frequency noise for the very small temporal scale, but so the reason to that is that as the observations are noisy and sparse, we add some noise at the high frequency, so we don't observe really the true underlying high frequency scale of the model. Also, one quick comment on that is that to produce this power density spectrum, we run the model over a lot of time step with no divergence. So it shows also that the model is very stable, which is actually the first things to try. If you want to see if you have a good model, you should run it for a long time to see if it's stable. We have also computed the Lyapunov spectrum. So I remember that we have already looked at the first Lyapunov exponent, 167. but we see that all the positive Lyapunov exponents, which represent the unstable part of our system, are quite well reproduced. It's not such a case for the negative, and even more for the neutral Lyapunov exponents, which represent the stable part of the system. And so it shows that we are reproducing well the unstable part, and we have some bias to represent what is stable in the system, which is quite similar to what has been shown in Patak, the Patak paper also. Okay, and here you see that we already saw this plot. So this is more about the forecast skill. We see that when we start at the same initial condition, and here's the difference. You see that until two Lyapunov time steps, you have a quite you have some forecast skill until two Lyapunov spectrum. Of course, we have also conducted some sensitivity to the observation, because the point is what we can do with the observations. So we have play with the observation error and play with the density of observations. I will not maybe go into too much detail on those slides, but yeah, we see that the system is quite sensitive to observation error and less sensitive until a certain point to the number of observations. So that concludes my first part, and I see that I'm already very long. But as I told you, maybe if you have one or two questions on this first part, I can answer question on that, and then continue to the second part.
Yes, thanks, Julien. I just noticed one question in the chat from Tainmoy, but I guess maybe you gave the answer.
Yeah, I saw this question pop up, and I've tried to answer while I was talking. So
yeah. And finally, I also had one question concerning the sensitivity tests, and you answered it in the end of this first part of the presentation. Because
okay.
I was just thinking also that maybe with too sparse and noisy observation, DA will not be successful enough to enable the machine learning cycle to provide a good emulator. But
yeah, that's
I guess.
Yeah. Actually, what we have observed, but we guess it's specific to this system. So I won't say that it's generalizable to all the dynamical system, but we say that we are very there is very few sensitivity to the density of observation until a certain point. And at a certain point, if you have too few observation, you cannot retrieve your dynamical system. So there is it's like a nonlinear dependency. So you are not sensitive, and then suddenly it becomes problematic. And regarding the noise, it's more continuous. The more the noise is increased, the more sensitive you are.
Yeah, okay. And do you think it can easily be applicable on higher dimensional system?
Yes, I think so, because we have evidence that data simulation can be applied very efficiently in a high-dimensional system, and also evidence that machine learning or data-driven models can be also applied to high-dimensional system.
Mm-hmm.
So I don't see any limitation in theory, but of course, when you come to practical problems, then you will have some problems. But maybe I can escape a bit on that question and say that the second part of my talk may be more relevant for high-dimensional system, because you will leverage on what you already know of the model. So your starting point is better.
Because I guess in higher dimensional system, you'll need to provide a more complex machine learning model with more parameters, and if the DA cycle is not accurate enough, probably the machine learning cycle will not be quite good as well. So I don't know, but we'll see the second part of your talk.
You're true, but the thing is, if your system is very complex and you have very few observations, and each observation is very noisy, it will be very difficult. So
yes, of course,
something has to go well. So you have to observe to have a good density of observation, a good first guess for your model. So in the second part, I will address the case where when you have a first guess for your model, so you know already something on your model.
Okay, thanks. I think Dion, you have a question also.
Yeah. Hi, Julien. Thank you very much. I have a question. How do you initiate the model and the state in the first cycle?
Sorry, can you repeat, please?
Yeah. How do you initiate the model and the state in the first cycle? Because we need the model to do assimilation, and we need the state to do identification.
Yes. Good question. So there are several ways of doing that. So in that case, we initialize the model randomly. So not the model randomly, but we initialize the weights of the parameter of the model randomly. And we use this bad model or this random model to do our first DS cycle. The other way to do it is, in our case, the observation operator is only a sampling operator. So we observe directly a noisy state. So we can, as you see here, sorry. No, it's not here, sorry. Here, yeah. We have performed an interpolation, spatial and temporal interpolation of the observations to make our first training.
Okay, thank you very much.
Okay, so as I see that the time is running, I will go to the second part, which is a bit newer. And actually, the framework is a bit similar, but a bit different. So now we assume that we know partially the system dynamics. So if you want to have to run your model on the integration time step, so we'll consider discrete time integration time step. So if you want to have the estimation of your state after a small delta t period, so which is the integration time step, we suppose that it is the sum of a model, a physical model m phi, which is known, and another part which represents all the dynamics which is not resolved by the physical model. So it's an unresolved component of the dynamics. And so we assume that we know this phi, m phi, so the physical part, but we will try to infer the unresolved component using data. So approximate m un, m unresolved, by a data-driven model. And we will also do that using a neural network. So this m unresolved will be represented by this m theta. So I'm sorry for the notation. So the theta here was called w in the previous part, but there are also the parameter of the neural net. And actually, this is also an idea that have been applied in some of previous work. It's even a bit older than what I've shown before, but here again, it's not comprehensive, so it's not complete. But you have those different, very nice paper which have done that. But what they have done is they have two versions of the model. So they have a coarse resolution model, which I call here the physical model. But they also have a high resolution model. So they know the truth. They know what they need to represent by the neural net. And actually, it's not always a neural net because, for example, Gorman and Dwyer use random forest to do that. And quite interestingly, because here it's the OceaniX project, so Bolton and Zana did that in the ocean. The other, it's more about cloud parameterization. But so to do that, to do what they have done, this author, and there are a lot of more results on that. They use a high resolution model, which are very expensive. And especially if you want to do some coupled model, where there is a coupled dynamics with both fast and slow components. And also you have no guarantee actually that this high resolution model are a good representation of the truth. And they will maybe not converge toward the observed state. So here again, we will. So yeah, no. So yeah. So here again, we will try to determine this unresolved part of the model using sparse and noisy data. So instead of using a high-dimensional model as it has been done in the paper I've shown you, we will try to use noisy and sparse data to determine the unresolved part of the model. So some few comments about that. Imagine that your physical model is in some way hard-coded in the neural net. So actually, we have the same setting as the setting before. So because in the first part of this talk, we have a neural net that emulates the whole dynamics. But if you say that within this neural net you have a part which is hard-coded and which represents the physical model, you can do exactly the same approach as in the first part. But it's very costly in general. So you have to imagine that you have to code a full model, a full physical model. So for example, NeMo within a neural net. So I don't know if it's quite realistic for a real world model. The physical models can be complex, and yeah, it's maybe not feasible to hard code it in neural net in general. I mean, but that could be a way. I know that in MIT they are trying to code their numerical model, physical numerical model in Julia, for example. So maybe this is the way to go. The second problem you have is the time step of the observations is usually larger than the integration time steps. So even if you have perfect observations, you don't observe what you have. So you don't observe, I come back a little bit, you don't observe this xt plus delta t at each delta t. You observe it at observational path times, which are in general much larger than the integration time step. And of course, except if you have hard-coded your physical model within the neural net, you cannot, in general, compute, or it's very difficult or very costly to compute the gradient or adjoint, which is called adjoint in the data estimation community of the physical model. So what we'll try to do now, this being said, we will try to propose an approach, given some simplification, of course, that does not rely on the adjoint of the physical model. And we will also try to propose an approach where the training of the neural network, so the training on this unresolved part, can be made separately from the integration of the physical model. So why we do that? Because if you have a very complex physical model, you can still use this physical model. So it's code on Fortran, you run it as you used to run it, and then you use the output of this numerical model to compare with the observation and to train your neural net. And actually, this kind of setting has been already, and learning the unresolved scale or the model error has been done also in very data assimilation perspective quite recently in this nice paper Bonavita and Laloyo 2020. And I will present something very similar to what they've done. So it's another paper which is in press, but you can find it on archive right now if you're interested to have more details. And so we have some observation. So I didn't put again the observation operator, the noise of the observation, but this is very similar to what I've shown in the first part. But what is new is that you observe your system at big data t, which is correspond to NC integration of the model. So I will here show a simplified description of the algorithm, but you have a more described and more accurate description in the paper. So what we do. So here again, I remind you that we want to estimate this m theta, which is an emulator for the unresolved part of the model. So first, we forecast the physical model only, m phi, on the NC time step. So to have a forecast xf that is at the time step of the observation. So you have a forecast at the observation, and so you have a forecast. You have an observation, so you can use a standard data assimilation procedure to have an analysis at this observational time step xk plus 1. Okay? So now we have to make some assumption, because as I said, I don't want to rely on any gradient of the physical model. I want to be offline. So I have to assume that the true state at t plus big delta t, so at the observational time step, is the sum of the integration of the physical model plus mc time the integration of the unresolved model. So this assumption here is a very strong assumption. It means that delta t is small enough so that the integration of the physical model and the integration of the unresolved part of the model are independent. It's a sum of both, and also that the unresolved part is not too non-linear. Is assumed to be too close to the linear during the small time delta t. So it means that you still need to have observational time which are not too large. And then once we do this first assumption, we have a second assumption which says basically that our analysis, so what it gives by data simulation, is the best version of the truth that we have. So we say that it's close to the truth. And once we have done that, you can train your unresolved part by minimizing the difference between the forecast of the unresolved part, MUN XK, and the target, which is the difference between what has been forecast by the physical model, XF, so this is a forecast by the physical model, and the analysis. So at the end, it comes out with a very simple idea. So we just try to learn which is called in data simulation, analysis increment. So we try to learn what has been modified between the forecast and the analysis through the observation. So this is what is done, for example, in the Loyo paper, but I have to stress here that doing that is equivalent to make those linear assumptions. So I don't say that the model is linear. I say that it's on delta t, it can be approximated by a linear model. And then you can train your neural net by the difference between your target here and the output of the emulator. And then once you have done that, so you have your physical model M phi, you have your unresolved scale model, data-driven unresolved scale model M theta, and you can produce new simulation, for example, to make forecasts. So this is the approach. So some quite quick comment on the setup. So we use ENKF to do the data simulation, and we have 3 layers neural net. I will come back very quickly on that. Yeah, and so we try several. We try also a hybrid model using the real true value. So we have a case where we have perfect observations, because we are in here again in a twin experiment setup. So we know what should be the truth. So we can use it to train our model to see it define an upper bound for our model. Also, if you look at what is the target of the neural net, so this is a difference between the analysis, so this is a corrected state, corrected by data assimilation, by assimilating the observation, and this is the forecast. So here there is an error between the analysis and the forecast. So the error is due to the error of the model. So the forecast does not give you the same thing as the analysis because there is an error in the model. So this is what we want to achieve, to estimate. But there is also an error in the initial condition, initial condition. So there is both error, model error and initial condition. So sometimes, so here we assume that initial condition error does not play a huge role and are neglectable in this term. Of course, this is not true, and sometimes we have to filter out those errors. And so we make an additional assumption here. We suppose that the initial condition error, so this is done also a lot in data assimilation communities, the initial condition error appear to be more as a high frequency. So we filtered also our analysis time series. We use a low pass, simple low pass filter, but I guess we can imagine something more elaborate. And we produce a time series. So this smooth time series is supposed to correct from the initial condition error. So in this smooth time series, we have mostly the error due to the model. So we have several experiments. One is with the two-scale Lorentz model. In the two-scale model, you have the physical model, which is represented by the large-scale model, which is very well known, or at least here supposed the dynamics. So I won't maybe detail too much because I still have to have time. But what you saw here is when you apply this technique, so training your neural net using the analysis increment, you can produce an hybrid model which has good forecast skill until 3 to 4 Lyapunov exponents. So here you have the forecast skill with respect with the lead time. So you see in green the forecast skill of what I've called the upper bound, so this perfect model. So this is a hybrid model that have been trained with perfect observation, no noise and no missing data. On the red curve is the forecast skill of the physical model only. So you don't correct this physical model by an unresolved by So this is the other curve. You improve a lot the four-time skills by adding this data-driven term for the unresolved part of the model. And what you see here also is that the number of observations, the density of observation, does not play a huge role in this skill. But what play a huge role is this observational time step. So we see that we make some assumption that the big delta t, so the time step between two observations are not too large with respect with the non-linearity of the unresolved scale. And we see that actually if the observational time step increase, you have an increase of the forecast skill or error. So you have an increase of the error, so decrease of the skill actually. So an increase of the error of your hybrid model. So the orange is the hybrid model made with sparse and noisy observation, and green is the hybrid model done with perfect observation. We also made another experiment with a bit more complex model. So it's a coupled atmosphere-ocean model called MAUAM. Sorry, MAUAM. Which is an atmosphere-ocean coupled model with 2 layers on the atmosphere, 1 layer on the ocean, and with also thermodynamics terms. And here we have a variables that are not present. But we will try to emulate those higher atmospheric variables using a neural network. So here we assume that we observe both the ocean and the atmosphere. And here the model is defined in spectral space. So we use multi-layer perceptron. Everything is connected to everything. We can discuss later on if you're interested by this locality. If you are defined in space, you can use convolutional neural networks to have locality. But here it's not the case. So you see that you improve your forecast skill. So we compare here the truncated model, the forecast skill of the truncated model after 2 years in the ocean and 1 day in the atmosphere, because the temporal scales of predictability are quite different in the ocean and the atmosphere. So the truncated model, you see here, the hybrid model learn with perfect observations. And here, most importantly, the DA hybrid, so the hybrid model learned using the training on the analysis increment. And you see there is a huge improvement of the forecast skill, especially in the ocean. The improvement is not that important in the atmosphere, but I just have to stress here that the time step of observation is 27 hours. So the atmospheric modes are not well represented. But here it's quite interesting because what's missing in the model are the atmospheric modes. So you cannot represent easily the atmospheric modes, the unresolved atmospheric scale, but what you represent is the effect on this very fast atmospheric scale on the ocean. So we improve the ocean forecast by have a better parameterization of the atmospheric modes. And so this is the forecast part. Do we have a better model? I always come back to those two questions. And so here I will show you the model attractor. So the evolution of the model in the phase space with respect to two variables. So here on the x-axis you have the first atmospheric mode, and on the second axis the second oceanic mode. And here for the true model you see what the attractor should look like. So you have this kind of repartition of the points in the phase space. Here you see what the attractor of the truncated model. So it's you see that actually the truncated model is a whole different model. It does not. The attractor is very different from what you have seen on the truncated model. You see that when you go to the hybrid model, you correct partially, but you correct partially the attractor. So the attractor of the hybrid model learn with perfect ops, or the hybrid model learn with data assimilation. So noisy and noisy ops here, they are not sparse, they are only noisy. You have reduced the difference between the attractor. Of course, there are some states that remain out of the attractor, but fewer than you have in the truncated model. So I will finish now because I think I'm very much. I've been too long already.
No, I think it's okay, Julien. No problem.
Okay, thank you. With this new result, so it's a bit it's a result that has been done by a student, Arthur Philloche, who have started his PhD in Leipzig in Sorbonne University, and he has deal with a case where you have also noisy observation, but you have a very specific type of sparse observation. You have a case where some variables of the model are never observed. So here it's an advection model. So you have a passive tracer here that is advected by a velocity field. The velocity field is also advected by itself. So there is an advection of the velocity field. But you never observe the velocity field. You only observe what you only observe is this passive tracer. And so this is the model. So here you have the advection of the tracer, the equation for the advection of the tracer, which is supposed to be known. And here you have the advection of the velocity field. But here you assume that you don't know that, and you never observe it, and you don't know the model here, which is in reality here, because it's always a twin experiment, which is also an advection term here. So you have a model which is also a sum of a physical model and a machine learning model. So the machine learning model is the advection of the velocity of the motion field. So the goal is to training a neural network to represent this non-resolved part of the model, but this non-resolved part is applicable to the motion field or the velocity field, which is never observed. So what is the technique? It's also a balance between an alternance between data assimilation and training of machine learning. But here the originality is, so the machine learning techniques here is for DVAR, but you train your for DVAR I was muted, right?
Yes.
Yeah, sorry, there is a problem from my side. Sorry, Julien. But it was just 5 seconds, I guess.
Okay. So I say that you first do your FORDIVAR on the dotted box here. So you have an estimation of with FORDIVAR by observing only the, even if you observe only the passive tracer, you have an estimation of both the passive tracer and the motion field, WT. And then you do the data, the FORDIVAR on the windows, but shifting by 1 time step. And then you have an estimation of the other velocity field here. And so you can train your neural net using those 2 velocity fields, WT and WT plus 1. So you train to predict WT plus 1 using WT. So ML of WT should give you WT plus 1. And then it's a cycle. So you put the model you have trained here, you push it back in the full model. So the full model is a hybrid model combining the physical model MP and the machine learning model and theta. And then you do again a FORDIVAR and you cycle several times to have until convergence, to have a good estimation. So if we can see that as a mix of my 2 parts actually. The first part was about cycling data assimilation and machine learning. So here it's what is down, but you apply it for only parameterization of a part of the unresolved part of a model. And also, what an interesting part here is everything has been done, including the FORDIVAR, using PyTorch, using automatic differentiation tool present in machine learning libraries. And so here again, we just assess the forecast skill. So we look at the forecast skill of the physics only model, so the truncated model, the forecast skill of the model trained on the perfect data. So here I remind you that you don't observe the velocity, but we have trained Arthur have trained a hybrid model using only with perfect velocity field. So assuming that you know, so this is the best. You cannot have best than that because here you observe the true field, and here you produce the hybrid model by observing only the tracer. And these are the results. So there is an uncertainty here because this is a forecast produced on several initial steps. So here we put for to mention it the persistence method. So assuming that everything stays the same, so the forecast is equal to the initial state. Here you have the RMSE with respect with the time of the physical model. So you see that as everything increases with time, of course, but it's increased much quicker than the hybrid model using by observing only the tracer. And here you have the hybrid model that you could achieve if you observe the velocity field. So I come to my conclusion. So in the part 1, I have shown how to build a surrogate model from partial and noisy data. We see that we have good reproduction of the slower scale, which are the more energetic also, and a good reproduction of unstable Lyapunov exponents. And the method was so sensitive to data noise and less on data density. In the second part, I've shown that we can build a hybrid model made of both a physical-based part and a data-driven surrogate of the unresolved scale, even if the case where you don't observe we don't observe some of the variables. That the method is quite sensitive to the temporal density of observation, but it's expected. If you want to train a data-driven model, the minimum is to have some observation that allows you to represent the dynamics of this dynamical model. And I have to stress that the approach I have proposed does not need any adjoint for the physical model, and can be performed independently of the physical model. We have still some question about the computing resources needed to compute this physical model, because the machine learning framework and the physical framework are very different. So we have to switch at each integration time step. We have to switch between a machine learning forecast and physical forecast. So it's quite expensive actually. But I know there are a lot of efforts done in that direction. For example, some toolbox to have automatic Fortran code for neural networks. So you can just include your neural net within your traditional numerical model. So it's something that starts to be considered, but we didn't use that. So we're still in Python, and it takes some time. And of course, all that I've shown here is done with autonomous system. It means that during all the period of the training, and even for the forecast, there is no evolution of the forcing of the model. So the model are autonomous. But of course, if you want to apply that to for example, ocean dynamics or atmosphere dynamics or climate dynamics, there are some forcings that evolve in time. So you have to address this problem at one point. So it's a problem I'm very interested in, and a second point, which is related. Actually, I think it's related. Is the estimation of the uncertainty of those estimates, which is not done here. All the models I have shown are deterministic, but I know there are some work that have worked on probabilistic models. So I think that's a good direction to go to this emulator. And I don't know if the slides will be put on the website, Maxime.
Yes, if it's okay for you, yes.
Yeah. So at the end, it's not. I will not comment it, but I have put a list of all the reference I have mentioned during the talk. So for people who want to see all those nice paper, it's a lot to read, but there are a lot of very good paper. I don't mean necessarily mine. There are a lot of interesting things to read here if you're interested in this subject. Yeah, and I'm finished, so I'm ready to take some question.
Okay, so thanks a lot, Julien. I saw that there are some questions on the chat,
Yeah.
and I think it's Yikun. If you want to, you can speak if you want, Yikun. If it's if you still have questions.
Hi, Julien.
Hi, Yikun.
Thanks for the talk. So it's very interesting. So in your last slide, slide 29, so you mentioned about the computational cost. So I wonder how is it large? How is it compared with the computation cost of a high resolution model?
Okay. So this problem, we have seen it on both Lorentz hybrid model and MAWA model. So it's very dependent. It's very dependent on the case. So it depends a lot of which is what is a high resolution model. But so far I have approximately a factor 1.5 more running the high resolution. 1.5 more running the hybrid model with respect with the high resolution model, but it's mainly due to the fact that so it's very technical. It's mainly due to the fact that the field has to be convert to tensor to be put inside the neural net of Keras, and then converted back to NumPy array, then to be run by the physical model. So all the time is spent on converting data types. So it's not a fundamental problem. It's really an implementation technical problem. If all the model was run on the same data structure and on the same language, it will be more. I think it will be a bit more efficient than the higher resolution model.
Thank you.
Hope it answers your question.
Okay, thanks. I think Sami, you also have a question.
Ouais. Salut Julien. I was wondering on your hybrid model part 2, is that correct to think that the ultimate goal, or at least a perfect hybrid model, would have a forecast skill as good as a reanalysis? Like to learn what the assimilation would do if you have the...
Oh, yeah. No, I don't think so. Because even if your hybrid model is perfect, so let's say we have the more perfect hybrid model we can hope, you will still have some difference between the forecast of your hybrid model and the reanalysis, because you have if your model has unstable mode, you will still have this initial condition error that will occur in the forecast. So you will still have some initial condition error to correct in the reanalysis. But if the hybrid model is perfect, the correction so it means that you have no more bias in your model. So you don't have bias to correct. You don't have model error. The only thing you have to do is to correct from initial conditions. So in terms of 4D VAR, for example, if you want to apply a 4D VAR, it means that you don't need to do a weak constraint 4D VAR. You can apply a strong constraint 4D VAR because you don't have no more model error. And if you want to do data assimilation, for example, it's done a lot data assimilation also to seasonal or to decadal forecast, and they have huge problem of model bias. And it means that if you use the hybrid model, you are not supposed to have model bias anymore. If it's perfect, of course. Yeah.
Okay, thanks.
Okay, thanks. We have another remark concerning ocean color in the chat. I don't know if you see that, Julien, if you want to react or not.
Yeah, so the question is, in ocean color, due to clouds, the data, are very sparse, and more often 10%, only than 50%. So it's Frédéric Jourdain who has the question, I guess. Yes, that's a very good point. Yes, but it doesn't. Okay, how to answer that? We cannot tell. This 50% is applicable to the Lorentz model. It doesn't mean that it's not applicable to. It doesn't mean that for other models it will be more 70% or 10%. So the key thing, I think, is if you want that the method work for 10%, if you have only 10% of the data, it means that you need to have observations that are more regularly sampled in time. So, for example, in ocean color, you can assume that you have observation each day, and if the emulator or the data-driven model you want to estimate is the time scale of this emulator of this data-driven model are much more than 1 day. If the time scale are 3-4 days, it means that maybe the method will work with less data. For Lorentz data, Lorentz model, for the Lorentz model, the model is very, very chaotic. So you really need some observation at small sample rate. But if it's a bit less chaotic for ocean color, maybe you can have hope for if you observe less than 10% data. But actually, that's a very good point. I'd like to try that on ocean color data.
Okay, thanks, Julien. I think Laurent has an additional comment on these questions, maybe.
It's mostly an impression that so the Lorentz model has some redundancy. There's a number of variables, but the effective dimension of the model is half the number of variables. So that's maybe something to have in mind. If you want to constrain a model, you need to have an idea of what is the number of free directions, the degrees of freedom, in the model. Then you would know, as we do in data simulation normally, that's the number of observations has to match that. So I think we are in about the same ballpark here. That was all.
Okay. I don't know if there is another question. Maybe I had another one, Julien. I think it was on slide 27.
Yes. Oh, yeah, sorry.
Yeah, with all this 4D-VAR combined scheme, I was quite interested by that because I think we are in this OceaniX framework interested in the same question. We are not currently trying to make some hybridization of models, but in the same way, we are trying to learn the dynamics based on sparse and noisy observations. And we also try to make our machine learning model converge with a gradient descent that is quite inspired by 4D-VAR. And I was wondering what type, I mean, even if you're using automatic differentiation tools in PyTorch, how do you learn and how do you model this 4D-VAR gradient descent? Are you using some sort of CNN or LSTM that is able to learn the 4D-VAR gradient descent and then you just have to apply it on new data sets?
No. For the 4D-VAR, we use a very standard 4D-VAR algorithm.
Okay.
Only thing is the gradient is computed by PyTorch. But beside that, we just define the traditional cost function for 4D-VAR.
Okay.
In that case, there are some additive regularization term, but this setup was done in a very classical 4D-VAR setup, and we took the same setup. And okay. So for example, the gradient descent technique. So I don't remember what optimization is done, but it's not a stochastic optimization.
Okay.
It's a very standard optimization. So there, but this is for 4D-VAR. But again, the machine learning training is done with stochastic gradient, so it's done in the most standard way for machine learning training. So here again, the two steps are different. We have on one side the 4D-VAR, which is a classical 4D-VAR. The only different here is that the gradient is calculated using PyTorch, but which is very convenient because in the hybrid model, you have a neural net. This neural net, anyway, as you need these gradients. So to do your 4D-VAR on the
okay. I see. So okay, I didn't get that. It's a bit different of what we're doing because from our side, we have a loss reconstruction in the classic neural network training, but we also have introduced some sort of 4D-VAR functional that we try to minimize in the neural network. And we are not involving any adjoint method. We are trying to learn how to optimize at best the 4D-VAR gradient descent, and it's done by CNN or LSTM. So,
okay. So you emulate, you're kind of emulating your 4D-VAR using...
Yeah, in fact, you're explicitly, it's not exactly a 4D-VAR function, but it's a similar functional between a compromise between an observation term and a prior term. And you want to optimize this gradient descent with a CNN or LSTM. But not to, and that's what is funny, it's not to optimize finally this functional, but it's to optimize the loss reconstruction. So you have this kind of compromise between this 4D-VAR function and the reconstruction loss in the neural network. So it's a pity that Ronan had to leave today, but I think maybe we could exchange later on this question here. Okay, is there any additional questions? Well, so yeah, probably not, but I don't know. Yeah, so as I just said, Ronan is not here anymore, but maybe we can have some topical discussions on these different aspects maybe next year when he'll be available, because I think we had a lot to share on these questions.
That's true. Yeah. Mm-hmm.
I'd like.
I think maybe if I can comment on
yes.
on one thing, which is not a question, but I think a more general comment I have is so we have a family of approach to have emulation for parametrization, for emulator, combining those data assimilation techniques and machine learning techniques. So I'm just saying a very general thing here, and I think which lack what we need as a community here, I think, is a good test case. I mean, a well-defined benchmark or well-defined test case where both, so for me, two conditions for best case test case will be: one, so the test case have to be useful. So so the traditional techniques, so if you do only data assimilation or if you use only the physical model, it's not enough. You need to do more. So this is, I think we need that. We need a test case which is useful for the community. And I mean the community more on the application side, so with a useful application, and also a test case which allows to be well described, well defined, with a good baseline, so people can take this test case and work on that. And I think a work that we could do as a community is to define those application case where we expect that those kind of techniques could be applicable. So yeah, it should be applicable and it should be useful. Yeah. And I think that the two questions we have to answer and to define new cases of application.
Yeah, I don't know if you're interested by that, but maybe Sami, if he's still here, can react. But we just started a data challenge based on SSH datasets. So it has been first initiated by teams in Grenoble. So Sami is well aware of that. And we made some sort of twin data challenge at EMT, but mostly for students on the more informatics aspects. But I think we have two GitHub repository with well-described problematics. The data are available, and if you're interested in, maybe you can just have a look, or I can send you the link. And basically, we have the data and working with different methods, some coming from the physics community, some coming from the machine learning community. So if you want to have a look, maybe I can send you the link.
Yeah, that sounds great.
Yeah, I just put the link to the GitHub repository.
Okay, yes, I can see it.
So it's mapping SSH from SWOT data or Nadir data. And it's going to evolve and have more, different problems, always in that topic of mapping surface variables.
Okay, but yeah, that sounds good.
Okay, thanks. That's fine for me. It's almost 3, so I think we are quite good for the moment. So yes, from my side, I will try to, I hope the recording of the video will be okay. I will try to make that available before the holidays. Julien, if you can send me the presentation, and I will make it available on the GitHub OceaniX repository as well.
I'll do that, yes.
Okay, so that's fine for me. Thanks again a lot, Julien. A very interesting talk.
Thanks for the invitation.
Yeah. So I hope we can exchange more next year, and maybe maybe a visit in Bergen would be great. I hope we'll see. We'll see next year in a non-confined setting. It would be better.
Yeah.
Okay.
Okay.
Okay. Thanks a lot, everyone, and especially Julien.
Thank you.